So today we'll be talking about this stability analysis prerequisite video part, and let me just see if possible we'll just get into the stability analysis section as well. And I have written down all the notes so that I will not spend time in writing all those points. So instead, it's all been listed, and I'll just glance through each of these points, and then, if possible, later we'll have a discussion on the Q&A session with Zoom. So with that being said, let us begin with this prerequisite part. So, in the prerequisite videos, we discussed about uh, the timing behavior of both first order and second order LTI system, where we used an S spline to analyze the timing behavior, whereas uh, the later part or the second part of the prerequisite video had a discussion about the frequency response of again both the first and the second order LTI system, and we used Bode plot in that case in order to analyze those behaviors. And today it will be a summary of both these analysis in a single video. So, we'll just begin with this timing behavior, where in this timing behavior we begin with a step input. So, consider any LTI system, and this LTI system has some transfer function which in time domain I will write it as small h of t, or in terms of frequency domain or S domain it could be written in capital letter. Okay, so that's the only difference. Now, so what happens is that to this transfer function, which is an LTI system, or to this LTI system, when I apply a step input, the output basically contains two component. If I plot with respect to time, so this is my V in versus the time, and this is my V out versus the time, and the output in general will have a behavior. So let me mark this particular point as 0. So with the same 0 point, I will have an output which will be initially 0, and then the moment it sees the step input, this particular step input has an infinite frequency range in it. Okay, a single step, when you just make a Fourier transform of this single step input, you will find all the frequency component. So basically it's a signal with infinite frequency range contained in it. So but the LTI system has some sort of poles in them, so these poles will generally restrict uh, the response at the output, which means that it tries to say, for example, I have a low pass filter. So basically the LTI system will have some sort of low pass filter characteristics, which means that all the high frequency signals will be filtered out when it passes through the LTI system. And when I try to build the same signal out of this low frequency component and leaving out all the high frequency component, the signal behavior would tend to have a kind of response which generally grows exponentially and reaches the final steady state. So one could split this behavior of this response, shifting from an initial value which is basically equal to 0 in this case, to a final value which can be the magnitude of this input signal, which is Vf, and this could be a gain times that of the Vf. Okay, so this medium has some gain, so let me write it as a naught, or some sort of gain, multiplied by the input magnitude, which is Vf. Okay, so this is the final value that I would attain, and during this transition from 0 to all the way to the final output voltage, one could visualize that there are two major components that are involved in this signal transition. Okay, and those signal components could be break down into what is known as a transient or natural response. The other one is the steady state or forced response. Now it's also been discussed in the video, prerequisite video, that the transient behavior or the natural response behavior is basically defined by what is termed as the system poles. So in general the system poles defines those transient behavior, so which means that I'm talking about this particular region where we call this entire segment as a transition, transient response or the natural response, and whereas the remaining part of this particular signal is taken as the steady state or forced response. Okay, so this particular behavior, the behavior where I just make a transition from one signal to a next signal level, we call this particular transition level or the response as something known as a natural response. Okay, now this behavior is basically defined by the system pole. Okay, And so in short, one could split this output behavior, which is y of t. So this is my y of t output, and for a corresponding input, I think I have used as x of t as my input signal. Yeah. So in that case, the y of t signal could be returned down into two components. One is the natural response, the other one is the steady state response. Okay. Now, and in general, the amplitude of this particular signal is defined by both the poles and zeros of the system. Okay. So basically the system output would be a magnified version of the input signal in general. Okay. So that's the reason why those two poles or the existence of poles and zeros of the system defines the magnitude of the output signal, and that is what is being stated in this particular line. Okay. Yeah. So we began with the discussion of a first order system, and we have taken a system having a transfer function in S domain as something like a divided by S plus a. For this, the output, when we feed this first order system with a type of input x of t, which is a step input, which is given in this pink color. Okay. So when I have this particular step input that has been provided to this, the output in general will have some sort of exponential graph, and one could define this exponential behavior with an output which is y of t, which could be defined as 1 minus e to the power minus a of t. So here in this case, this a is nothing but defines the pole of our system. So which means that when we try to plot in terms of a Bode plot, let me just use only the magnitude plot. I will have the other discussion about the magnitude as well as the phase plot of this Bode plot later on in the coming slide, but as of now I'll just give a simple overview of it. Okay. So where the x-axis is basically defined in terms of logarithmic scale of the frequency, and the magnitude plot would have something like this. So now in this case, the a is something, it defines a 3 dB frequency or defines the bandwidth of the system, and uh, when we try to plot the graph, in this case I am not plotting in terms of dB, but rather I am just plotting in terms of values. So I have a gain of 1 throughout this medium, and till I reach this particular pole location, I assume that the gain from the input to the output signal over this different frequency component remains the same. So this is something like an approximation that we are following it here, but in reality it never happens. The signal tends to get degraded, and when it reaches this particular point where I have a system pole, the signal would get degraded to a value which is defined as 0.707, which is nothing but 1 over square root of 2 value. Okay. Yeah. So due to which the signal basically makes a kind of transition that goes something like this, and then it moves at a rate of minus 20 dB per decade. But rather than using this kind of behavior that I have plotted right now, I would use a piecewise approximation, which means that I assume that the gain through the medium stays constant till I reach the first pole, and after then the gain would then degrades at a rate of minus 20 dB per decade. Okay. So this is the approximation that we will be following throughout the session. Yeah. So since because this particular LTI system has only a particular bandwidth of of this particular system, what happens is that all the high frequency component that comes out of this step input is been filtered out by this LTI system. Okay. So due to which the output in general will lag all the high frequency component, due to which it will have an output which grows exponentially, and the growth of this exponential graph is being defined in this way. And again, one could visualize this component as two different components, where the value of 1 denotes your steady state response, and the value of e to the power minus a of t defines the natural response of your output. Okay. And as we know that as time progresses, e to the power negative value will tend to make this quantity small as the time rises. Okay. So in general we know that e to the power minus infinity is nothing but is equal to 0. Okay. So, as the time approaches a very large value, then the entire quantity of natural response would then generally die out. Okay. Now, one can also make this natural response to die out faster, provided if this value of a is large. Okay. So, what I really mean by this large value of a is that I have to have a large pole or the large bandwidth in my system. So, pushing this towards the right would make my value of a to a larger value. Okay. So, in that case what happens is that uh, the transfer function in general tries to push all the high frequency component to the output. Okay. So, it will not filter the high frequency component, but rather it tries to pass all the high frequency components along the system. Okay. And due to which the response will further improve. So, as the value of a rises, generally the bandwidth of the system rises, and due to which the response of this will have a quick response at the output. Okay. So, the output will certainly get few more high frequency component, and due to which when we try to build them we will have a quick response, and that is what we really mean. Okay. Yeah. Now, based on this factor a, which is also termed as 3 dB frequency or bandwidth of the system, one could define two important timing parameters. One is defined as the rise time, the other one is the settling time. So, what I really mean by rise time and the settling time is nothing but the rise time in general is measured as the time it requires for an output to change from 20% of the value to the final value to the 80% of the final value. So, this is defined as the rise time, but in few other textbooks or like this is not a standard de facto method that 20 to 80% is measured as uh, rise time, but sometimes people tend to use even 10% to 90% as the rise time. So, the definition generally varies. Yeah. So, even this change in the value from 10% to the 90% of its final value is also taken as a rise time. Okay. Yeah. So, the other quantity that one could define is basically based on the settling time, and this settling time is nothing but it depends on the specification that has been given to a designer. So, we know that our output will reach the final state only when the time t approaches infinity, or the entire e to the power at term, this quantity approaches infinity, only then we will get a final value. So, in general the spec will define us that in order to the spec will define us such that it is enough to reach at least 95% or 98% of the final value. So, due to which the timing parameter that is required to reach this 95% or 98% of the final value will never be an infinite quantity. Okay. So, it all depends on the spec, and based on that one could define this settling time. Okay. So, this settling time in general is the time it requires for us to reach either to 95%. So, again it is not a standard one, or 98%. So, we know that in order to reach this 98% it requires a lot of time to reach that particular value. Okay. Yeah. So, a first order system in general defines a parameter, and which is nothing but the system pole, and that system pole in general defines two other timing parameters. One is the rise time, the other one is the settling time. So, now we will just make a quick jump onto this second order system, where we the system transfer function in general have two parameters. One of the parameter is termed as natural response or omega n, where there will not be any damping, and the other important factor or the parameter that can be defined by the second order system transfer function is the damping ratio. So, this damping ratio in general could be extracted by the simple formula, which is the exponential decaying factor divided by the natural frequency. So, here in this case I am not giving any formula for either for rise time or for the settling time or even for omega n and zeta, which is nothing but the damping ratio. It's only uh, the the knowledge that I want to you to involve to get involved in this rather than mugging up the values or the expressions. Okay, so it's enough if we get to know why the system is behaving, that is more than sufficient for us to proceed into the stability analysis. Yeah. So with that being said, so here in this case, the system transfer function having a second order pole is defined in this way, and one can also define in terms of A and B. Okay. So in the first case, the entire system transfer function is defined in terms of the natural frequency as well as the damping ratio, but in short, uh, the transfer function that when we try to analyze will not appear in this particular form, but rather in terms of the second form, and one could easily map these A and B terms in terms of natural frequency as well as the damping ratio just by making use of these general formulas that I have written down here. Okay. So by based on these things, one could really map onto this. Yeah. So with that being said, I will not go much in depth, but rather what I do is that let me try to use this damping ratio carrying different values and see how does the system poles will move around in the S spline, and depending on the location of these poles in the S spline, let us see the behavior of the transient response. Okay. Yeah. So in the first case, let us assume that the factor eta or the damping ratio carries a value of 0. So in that case, the system pole which has been written in terms of natural response as well as the damping ratio, and so based on this one could write the roots of this polynomial as this quantity. Okay. So please ensure that you have made a note of this roots, which is defined as minus eta omega n plus or minus omega n into square root of eta square minus 1. Okay. So we'll just use this particular quantity, and then later we'll just try to substitute different values of eta and see what happens to these roots and how does these roots gets placed on the S spline. Okay. And that is what we are going to discuss in the next following pages. Okay. Yeah. So in the case when the damping ratio is equal to 0, which means that we don't have any damping. Okay. And the poles will then be returned, or generally the roots of the polynomial will then have this particular notation where we have the yeah, I think it's a pretty simple straightforward substitution of zeta that is being equal to 1, and placing on this will make this real quantity to be 0, and again the square root of 1 would give us this j factor over here. Okay. Yeah. So so the same. Yeah. So due to which we have two poles, and these two poles will appear exactly on this j omega axis in the S spline. Okay. And the same when we look across the transient response or the timing behavior of the output, when I apply a step input to this transfer function, let me write it as h of t. Okay. And then I am trying to apply an input which is a step input, and the output of this step response will have this kind of output which is defined here as y of t. Okay. And that behavior is what is being shown over here. Okay. Now you could able to see, just because the system poles of h of t lies on the j omega axis, it has an output which generally oscillates at a particular frequency defined by this natural frequency, okay, omega n. At that particular frequency, this the output would then oscillate, and we call this response as an undamped response. Okay. And the next one is having a zeta value which is greater than a value of 0 and less than the value of 1. Okay. So when we use this particular value of zeta onto this roots of this polynomial, we generally end up having a complex conjugate poles. Okay. Now in that case, we have both the real part as well as the imaginary part in it, and the same when we try to plot on this S spline, we could able to see that this S spline has a real part as well as the imaginary part. Okay. and in general one could write this imaginary part as something like j omega d, just a short form of this omega n into square root of 1 minus zeta square, okay, just a short form notation which is written as omega d, okay. Otherwise this does not have any real meaning in it. Now in such case, when I apply a step input to this second order LTI system, the output y of t generally has this kind of response, okay, where you could be able to see that the output generally have some sort of peaking, and there is an oscillation that has been associated with this particular signal, and this oscillation is defined by this omega d. The frequency at which this oscillation happens is defined by this frequency omega d, and the rate at which this signal dies out or the oscillation dies out is defined by this real part of this zeta times that of omega n, which here in this case I have taken it as uh, sigma, okay. This sigma value is basically is nothing but zeta into omega n, and this quantity will define the rate at which this oscillation will die out, okay. So if this eta has a large value, then the rate at which this falls down will be much quicker. So we will not have much uh, oscillations at the output, rather, but the output in general will have a quick uh, settling down to the final steady state value, okay. So the oscillations will die out very fast is what I really mean here. So now generally it is this particular response we generally more focus on, just because uh, and we call this response as something known as underdamped, and as I said, in the case of an LTI system, in the case of a first order LTI system, we had a single parameter a, and that single parameter was utilized to define two other timing parameters. One is the rise time, the other one is the settling time, okay. Whereas in the case, this is for the first order, and in the case of a second order system, we have two parameters, one is omega n and the other one is the damping ratio. So with these two ratios, one could basically define three timing parameters, which is a combination of all. The one is again the rise time, the other one is the settling time, and apart from this we also have something known as peaking time, and this particular peaking time will generally appear only when we have a damping ratio that is falling within the range of 0 to 1, okay. So which means that whenever we have this underdamped condition, only then this timing parameter Tp will come into picture, otherwise we will not have this particular factor coming into picture, okay. Yeah, so and this is more important response, and we will be discussing about this response again when we discuss about the frequency response of the second order LTI system, okay. And next comes the damping ratio having a value of 1, okay. So in that case what happens is that when I substitute the value of zeta that is equal to 1, the this particular term will completely goes down to a factor of 0, and we will end up having both those roots appearing on the same location, which is defined as zeta times that of omega n, and again since the value of zeta is equal to 1, this will appear on the axis of omega n itself, okay. So as you could able to see, you could see that across this S plane we have two poles sitting one on top of each other, and the output response for a step input would then generally have this kind of output which is mapped onto this graph y of t, and we call this response as a critically damped response, where we have both the system poles of this h of t is placed one on top of each other, okay. And yeah, I forgot one more thing to tell. Even this x of t, which is an uh, input signal, which is a step input, also has a pole associated with it, and the pole can be read by translating this step input into a Laplace transform as x of s, and we know this for the step input it has a kind of response which is defined as 1 by s, and based on this one could say that the pole of this input function or the input signal appears at the origin, okay. So this 1 by s is again has a pole which exactly lies at the origin of our S spline. Okay. So in general, the S spline is used not only to plot the system poles, but one could also use to plot the poles of the signal as well. And that is what I really try to mean here. Yeah. So having said that, this is the type of response that we would end up having it. And as you could able to see that there is no peaking or no oscillation that appears in this case, just because we don't have this omega or any imaginary term associated with this roots of this characteristic equation of h of t, okay, due to which we never have any sort of oscillation in the output response. So the next comes a value of damping ratio. When we choose greater than the value of 1, then again when I look into this roots of the second order polynomial, we find that both these roots appears to be in a real value. Okay, so they never contain any imaginary part. So due to which one of the pole will be pushed towards the left side, whereas the other pole will push towards the right side. So the pole that is closer to the origin in general defines the bandwidth of the system, and just because it has been pushed towards the 0, the bandwidth of this second order system will become smaller. So as said before, whenever we have this LTI system having a smaller bandwidth, the output response in general will be slightly laggy, means the response will appear very slow. Okay, and it's just because of this particular pole that has been pushed towards the origin. Okay, and we call this particular pole which appears closer to the origin as the dominant pole. I think this one we have already defined or discussed when we discussed about frequency response. Okay, so we call this the one pole that is closer to the origin as the dominant pole. The other pole which is far away from this origin, we call it as a non-dominant pole. Clear? Yeah. So as you could be able to see that I have given two values of zeta, and when I have a zeta factor that is equal to 1.5, you could see that the response is bit responsive than compared to the response of zeta that is equal to 2. Okay, so which means that as the value of zeta becomes larger and larger, the output response will be much slower, just because the bandwidth of this second order system becomes smaller and smaller. Okay, and both these response will be much smaller when we compare to the critically damped response. Okay, yeah. So having said that, now that we'll just move on to this frequency response. In the case of this frequency response, we'll be studying about the steady state response of the LTI system. Okay, so as we know that in general the steady state response is basically defined by the poles of the input function rather than the poles of the uh, system. Okay, so we generally have two type of poles, one from the input pole, one from the input signal, the other is from the system itself. Okay, and a frequency response is something that basically studies about the steady state response, and we and in that case we generally will not discuss about this natural response or the transient behavior of the output. Okay, hope that you're clear with that. Okay, so what I really mean is that we'll be studying about the behavior of the output, if at all, if I have an LTI system. Okay, this LTI system will be right now provided with a type of signal which in general is a sinusoidal signal, and this sinusoidal signal will have an output which in generally we call this output as a kind of steady state output. Okay. So this output where there is a continuous change in the input signal creates a continuous change at the output signal is called as a steady state response. Okay, it is completely different, by the way, when we try to analyze the transient behavior, where we had an input signal which is transient, which contains all different frequencies or infinite frequencies inside this. Okay. Whereas yeah, so in the case of a transient behavior, we were using an input signal that contained infinite frequencies inside this, But right now when we try to analyze a frequency response, we pick a sinusoidal signal containing a single frequency. Say for example, I am oscillating at a particular frequency, say for example it is 1 kilohertz. Okay, it is only that particular frequency that is being applied to the system, and we will get an output. Since because the system is a linear system, the output will also oscillate at the same frequency, at same 1 kilohertz. The way by which the input and output differs is depends on two quantities. One we call it as the magnitude. Okay, the magnitude of the output response right now, this y of t, will be different from the magnitude of the input signal, provided if some sort of gain is applied through this linear LTI system. Okay, so in that case the magnitude of the output signal might change, and the other thing that you can expect as a change would be your phase. Just a second. Hello. Yeah, Ravi, I'm in class. You can call me later. Yeah. So yeah. So as I said, for a frequency response, the frequency of the input and output signal will be same, but the one that differs from the input to the output are only two quantities. One is the magnitude, the other one is the phase. Okay, so those are the two quantities that can vary between the input signal sinusoid to the output signal sinusoid. Okay, yeah. So and as stated here, the frequency response in general is the study about the steady state response, and for that, uh, in order to study about this y s of y suffix ss of t, which is nothing but the steady state response, depends only on the input pole of the sinusoidal signal. Okay, and it never depends on the system pole. But even though I say this, the y of t doesn't depend on the natural response, which is basically as we have seen that this natural response is basically defined by the poles of the system, but still these system poles defines some of the parameters in our frequency response, like bandwidth and even the resonant frequencies. All of these frequency components can be defined through the system poles. Okay, hope that you are I'm not getting I'm not making you to confuse here. So if you have watched those videos, then whatever I say here would be just a repetition of what we are seeing here. Okay, yeah. So 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 the next thing is that let us try to prove that the output will never depend on the frequency, but rather it depends only on the magnitude and the phase, or the output and input can differ only in terms of magnitude and phase. I just want to prove that with a simple transformation. So here I have taken a signal which is x of t, which is basically a sinusoidal signal oscillating at a particular frequency omega. Now the same could be written in a polar form, where we could translate this entire signal into a polar form in where the first quantity represents the magnitude of the input signal, which is defined as mi, whereas the second quantity defines the phase of this input signal. And that particular signal, when it is being passed through an LTI system h of t, then we will get an output. As I said, the input and output will differ in magnitude. Okay, which is in this case I have an input magnitude of mi, whereas the output signal has a different magnitude, which is m naught. Okay, and also the input signal has a different phase, which is phi I, whereas the output signal has a different phase. So in that way both these signals can change, but when we really compare the frequency of this input and the frequency of this output, they both will have the same frequency involved in it. Okay, and that is why we call this as an LTI system. Yeah. So now in order to translate this timing response behavior into what is known as a frequency response behavior, in order to study those behaviors in general, as I said, we have to map this S to j omega term, just because the sigma in general defines the natural response part, and we know that uh, in order to study the frequency response, we more focus on the steady state response rather than on the transient response. So due to which we generally define the sigma or the real value of this s term to be equal to 0. Hope that you are clear. So this in general will make this y n of t to go to 0, and that is what I try to mean here. Okay, and having this s trying to map only to j omega term would ensure that this particular response is not equal to 0. Okay, so we'll have a steady state response at the output. Yeah, so the same quantity that I have defined here, x of t, can be written down in terms of frequency of x of omega, uh, just by making this mi in terms of mi at a particular frequency. Okay, and similarly reading this phi term as phi I of omega. Okay, so I think these are all like just the uh, Laplace transformation between the input signal in terms of time domain to a frequency domain. Okay, so now in general one could define this output magnitude, which is m0 of omega, as a product of input signal magnitude times the amplitude, or basically the gain of the transfer function. Okay, and both these quantities would then multiply to create the output response magnitude. Whereas when it comes to the phase of the output signal is generally it's the addition of both the input phase as well as the phase which is nothing but the lag through the system, which is defined by this phi sub x of omega. Okay, uh, that is the phase introduced by the system. So both these phases has to be added in order to define the output phase. So hope that you are clear with this, and in general we will just add these two quantities when we discuss about causal systems. Okay, so which you would have learned in your signals and systems course. Yeah, so now in order to translate our signals in terms of x of t and sorry x of omega, we have to look across some Laplace transformation functions. So we know that the cos of omega t can be translated into a Laplace transform, something like this. Okay, s divided by s square plus omega square, whereas the sinusoidal signal could be defined as omega divided by s square plus omega square. Okay, and both these quantities could then be combined in order to create this signal x of t, and this input signal can be translated into the frequency domain signal just by substituting these appropriate quantities onto this particular signal. Okay, so it's just a simple math, or which you would have already learned in your basic mathematical course. Okay, so I've just converted my signal x of t in time domain to a frequency domain, or in terms of s domain, and in short, the output y of s, okay, or y of omega, could be written down as a product of input signal into the response of the system. Okay, so here in this case I know that the input signal has the form of x of s defined by this uh, particular quantity that I have substituted here, and that has been multiplied to the system transfer function, and later one could rewrite this denominator polynomial of the input signal, which is s square plus omega square, as two roots. One is plus j omega, the other one is s minus j omega. Okay, so one could split it into two roots, and that is how it has been written down here. And now that when we try to apply this partial fraction method, one could step down this input uh, signal or input poles. Okay, so one could actually split this input poles into two components, where we have k1 divided by the pole at j omega, and the other one is k2 divided by s minus j omega. So we have two type of poles defined in terms of input signals. Okay, so these are the poles out of my input signal, okay, not from the poles of the system. And we also when we apply this partial fraction method, the such of s will also have this partial fractions in defined in terms of system poles. But since we are worried about the frequency response, and in general the frequency response uh, will discuss only on the steady state response, will not majorly focus on this natural frequency or the natural response term that is defined by this h of s quantity. Okay, so we generally neglect this particular quantity and we'll just focus only on the steady state response, and due to which one could rewrite this y of s in terms of steady state response of y ss of s. Okay, and this is what we are majorly concerned in the frequency response. Now taking an inverse Laplace transform on this would then give us this entire quantity. Okay, so where you could able to see that I have a product of mi with mh, which is nothing but the input magnitude multiplied with the magnitude of the system, and the added version of both these phases of phi I from the input and phi h from the system. Okay, so in general the added version could be written as phi naught, and that is what is being plugged over here, and the product of this mi with mh could be written down as m naught here. Okay, and that is how I can define my steady state response. So here in this case let me concentrate only on the underdamped response, where there are certain phenomena that happens both in terms of time response as well as in terms of frequency response. Okay, so as we know that whenever we have this damping ratio which is equal to or within the value of 0 to 1, then this creates what is known as a complex conjugate poles. So as you could able to see that there are two poles which are complex conjugate in this case, and it has both the real part as well as the imaginary parts. Okay, so probably if this particular picture is pretty small for you, you can actually zoom in and see, or just carry out whatever I am saying. Okay, that is more than sufficient. So we have some sort of complex conjugate pole in an S spline. Okay, now having this kind of behavior will in turn defines an output response to have this kind of response for a step input. So this is the type of output that I would get as a step response. If my input signal is a step input, then the output signal y of t will have this kind of behavior where you would see some sort of peaking and then there is some sort of oscillation, but this oscillation will generally die out just because of the real component that we have across this particular term. Okay, because of this real component of our pole, system pole, this oscillation will die out quick. Okay, yeah. So this is the phenomena that we have studied with respect to a step input in the timing response. But what happens in the case of a frequency response is that, as we know, that these system poles in general defines the bandwidth of the system, right? So which means that I will have a pole, and in that particular pole we know that there will be a decaying factor that happens after this particular pole. The magnitude of the response will be same, but once I cross this particular pole or the bandwidth of the system, then the magnitude of the response will then degrade at a particular rate. So in this case, since we are dealing with a second order system, the rate at which this magnitude would die out or fall basically will be at a rate of minus 40 dB per decade, just because we have two poles in our system response. Okay, so hope that it is clear to you. But whenever we have a specific value which ranges from 0 to 1 for the factor of damping ratio, you could see some sort of peaking happens even in the case of a frequency response. Okay, the peaking not only happens in our time response when we have a zeta that falls between 0 to 1, but one could also visualize that some sort of peaking happens even in the case of a frequency response. So there is some sort of correlation that happens between both this time response as well as in the frequency response. even though the input signal to the time response is a step input, whereas the input signal to a frequency response is a sinusoidal input. Okay. So also one could see that this factor zeta, when it is quite closer to the value of 0, there is a sharp change in the phase from 0 to 180 degree, because each pole will induce a 90-degree phase shift, and since because we have second order system, it has two poles, and these two poles will have a sharper response, or will induce a sharp change in the phase when we have zeta that is closer to a value of 0. But as we relax the value of zeta to a much larger value, then the rate at which the phase changes will also have a greater slope. Okay, and that is what has been pictorially been represented over here. Okay, all these discussions are already been done, but just a quick review that I am trying to make. Hope this review is helpful to you. Yeah. So and also there are a few terms that I need to bring out of this frequency response. Um, as we know that the bandwidth of the system is defined uh, as omega 3 dB, and it is the frequency at which the DC magnitude reduces by a factor of minus 3 dB, right. So and when we look carefully here, we have this one more frequency term that appears into this frequency response when I have an underdamped response. Okay, it's only for underdamped response we have this resonance, or we call this particular frequency at which this peaking happens as resonant frequency. Okay, so we have this resonant frequency term appearing only for a system that has an underdamped response. Okay, and this resonant frequency term will not appear for other type of responses. Okay, so let me write that. It is only for underdamped response. Okay, so it is almost similar to what we have discussed. We also had discussed about uh, TP, or the peak time, which is defined as the time at which the peak happens. Okay, so even this TP value will appear only for a system that is underdamped. Okay, and it will not appear for other type of response. Okay, so yeah, and one could see that there is this particular frequency, which is the resonant frequency, is different from the 3 dB frequency, where the 3 dB frequency is measured at a frequency where we have the response is equal to zero 0.7, or is reduced by a factor of 3 dB from our DC gain. Okay, so both these omega bandwidth and omega r will be different. Okay, and sometimes they may overlap, or sometimes they tend to move towards the right or left, or sometimes even this omega r will never appear. Okay, so we will not go much into this discussion, and this is the type of response that we would get as a frequency response. And next comes the same thing. Okay, so for a second order system, we have this purple color, or the the purple color denoting a complex conjugate pole, but with a smaller magnitude of real part. Okay, so here in this case the real part is small, which means the rate at which it dies out would be pretty small. Okay, so it takes a longer time for us to bring this oscillation to step down when compared to the other type of pole locations, whereas in this case we have a real part which is quite larger than compared to the previous real part, due to which the rate at which this second signal, this particular signal would die out, would be much faster than compared to the previous signal. Okay, and as we move further and further, when we have this I think this orange one, let me use a different color, I guess. Yeah, so when we use this orange color, you could be able to see we are under critically damped condition. Under this critically damped condition, you see that the response will not have any sort of peaking. Okay, so no peaking will happen when we are at critically damped condition, and the output would respond bit slower than the underdamped condition. Okay, I will not reach the output fast. Okay, it takes a bit of time, and as we move further towards the real part of the S spline, then the response will be further laggy, and we will reach the output in a much slower phase. And accordingly, all these frequency response, where we have the top graph talks about the magnitude plot of it, and the bottom graph discusses about the Bode plot of the phase. Okay. This is nothing but the phase plot. Okay. Yeah. So these are the type of Cara that we would end up, and let me conclude this session with just a quick review of Bode plot in case if you are unfamiliar with it. Uh, a Bode plot in general consists of two plots. One is the magnitude plot, the other one is the phase plot, where in the case of a magnitude plot we have this y-axis defined with in terms of magnitude in terms of dB, whereas the phase plot will have the y-axis being defined in terms of degrees or the phase angles. Okay, and the x-axis of both these graphs will generally have this logarithmic scale of frequency. And now when we take a system having a transfer function which has just the DC gain. Okay, so let us assume that we have a system h of s, and that system has just plus k. Then in that case, the output response would be defined by this first set of graph, where there is no phase difference between the input and output of our system. Okay, so since because of this plus signature, there is no phase difference between the input and output, and due to which the phase response will be equal to 0. Whereas in case if we have a DC gain which is just minus k, and there is no frequency dependency term associated with it, or which what I really mean is that if there is no pole or a 0 in this transfer function, then the output response will still have the same value of constant DC gain throughout the entire frequency, but the phase angle will be different just because of this negative sign. There will be a phase shift of 180 degree between the input and output. So what we really mean is that when I have a positive cycle followed by a negative cycle, the output will have a negative cycle followed by a positive cycle. It's something like a CS amplifier, which is an inverting amplifier. Okay, and that is what we really mean by this. So there is clearly a phase shift between the input and output signal by an angle of 180 degree. Yeah. Uh, so in general, the system transfer function will have a notion like in this case there is a DC quantity of k, and there is also a 0 associated with this system, and there are two poles in our system. One, the pole is at 0, the other one has a pole at p1. Okay, and we call this type of how to say this type of transfer function as pole 0 form, and they are generally used when we involve ourselves with the S plane. Okay, but when we one can also rewrite this transfer function in terms of what is known as time constant form, and we generally use this time constant form when we try to plot them in terms of Bode plot. Okay, so this is a Bode plot, and whenever we want to plot a Bode plot, it is better to convert your transfer function in terms of what is known as a time constant form. So it is nothing but pulling out the poles such that we end up having S divided by the pole or S divided by a 0 term. Okay, and this type of form is known as the time constant form. Okay, and whenever we go for a frequency response, then we just map our S term to j omega term, and then we try to write down this transfer function in terms of j omega. Okay, yeah. So hope that we are running short of time. So maybe you would have seen those videos. Yeah. So I think I'll just stop here, and I'll just send you the link of Zoom video so we can have a Q&A session over there. Thanks for attending. Thank you.